Well, good morning, everybody.
Morning.
Happy Thanksgiving.
Happy Thanksgiving.
Yeah, I wish I could have made it so that you guys didn't have to come in today, but that is not within my power. But what's happening tomorrow?
You're sick.
I'm sick tomorrow, right? So remember that it's just Mr. Balogh's class that's not happening. I'm not responsible for your other classes, and I'm not responsible for you missing your other classes, right? But there will be no lab tomorrow. I won't even be on campus. I'm just taking one of my sick days. And actually, I'm going to the doctor. So not that I'm sick, but time for a physical. Old man, got to poke the old man.
Physical.
Yeah, physical. Yes, thank you. At any rate, I won't be here. Have a good Thanksgiving and be safe. Excuse me. We need to finish up the laws of thermodynamics. And we're going to go to the second law of thermodynamics. And we're going to tackle this one. This is going to be weird. Because if you've been in chemistry, then you've studied the second law of thermodynamics. I know you have. And this is going to take us to like entropy and all kinds of things. But I'm going to guess that what we're going to talk about today is going to be pretty new for you. Okay? And so there's going to be, by the time we're done, there's going to be 3 different statements about what the second law of thermodynamics is. We'll start with the one I think that chemistry kind of starts you with, and then we'll move into the more physicsy parts of it. Nature follows a pattern. And the pattern when it comes to energy transfer is that heat always moves from hot to cold. It does not go the other way naturally. We can force it to go in reverse, which is what a refrigerator is. But left to its own devices, right? If I set an ice cube down on a table, what's that ice cube going to do? It's going to melt. As long as the air temperature is high enough, right? It'll melt. Will it ever cause will the ice cube ever suck in more cold?
Whoa.
If it just sits there.
It can't suck in cold.
Yeah, it doesn't suck in cold. And that's kind of what the second law of thermodynamics is trying to say. Okay? It's going to heat always flows from the hotter thing to a colder thing, not the other way around. The ice cube's not going to cool off the table directly. The table will become colder because thermal energy is coming from the table into the ice cube, so on and so forth. So that's interesting, but for a physicist, what really matters is what can you do with that information. In physics, we're all about what can we cause to happen based on our knowledge. And we've been doing it all semester long. We did it with kinematics, we did it with Newton's laws, momentum, energy. All of these toolboxes we gave you were all kind of designed or made with this idea of what kind of motion can we cause to have happen? What sort of power do we have in being able to predict what's going to happen? These are all things that physicists are wanting to do. And so we're going to talk today almost exclusively about heat engines and refrigerators. We're going to talk a little bit about the engineering, but these are ideas. These are schematics. These are broad concepts about how do we take advantage of the second law of thermodynamics, where heat naturally moves from hot things to cold things. So is there a way to capitalize on what that is? And the answer is yes. We can make a heat engine or a refrigerator. So we'll start with the heat engine. Again, this is an idea. It's not an engineering diagram, okay? But the engine is this kind of square thing in the middle, okay? Engines produce work. And to help you, I'm going to ground this in an engine that you are probably familiar with, maybe not the nitty-gritty details of it, but one that you very likely use every day, which is a car engine. Okay? So let's talk about how your car engine works at a very broad level. What do you burn in a car's engine? Gasoline. So the gasoline is burnt and becomes very, very hot. Okay? That heat is then used to do work, the work of getting your car to go forward. But there is a exhaust that happens. And where does the exhaust in your engine go? Out the tailpipe. Okay? So, oh boy. So like if this were a gasoline engine, right? We burn the gas and that causes a hot temperature thing to happen, okay? The job of the engine is to take that heat energy and produce some work. And again, we're not going into the engineering yet of how that happens, okay? And then whatever can't be used to make work is called exhaust. It's had heat extracted from it, so it is colder, which is why you'll see symbols like Q low and Q high, right? Q hot, Q low. Anybody that's ever made the mistake of touching your exhaust pipe while your car's been running knows that that's not cold, right? You'll burn your hand if you grab the exhaust pipe while the car's running, okay? But it's colder than the internal parts of the engine, okay? And that's kind of the key. But there's this flow of energy, right, moving through the engine, and what we're doing is we're picking off a part of it and using part of that energy to get the car moving. So this is the broad concept of any engine, car engine, airplane engine, lawnmower, right? We're just trying to get some sort of physical work out of a flow of thermal energy. And so we write down statements kind of like this, right? So for an engine, the amount of work that comes out, let's just like borrow from like the first law of thermodynamics or conservation of energy, okay? And let's just do some what ifs. If I put 100 joules into the engine, okay, and 90 joules of exhaust comes out, how much work did we get? 10. Conservation of energy. Like, where did the 10 go? Well, the 10 must have gone into work. So the amount of work we're going to get out of our engine is going to be, and these are written kind of strangely, QH in absolute value minus QC. Now, what's going on here? We're using absolute values to ram home the idea that it's the amount of energy that matters, not necessarily the direction the energy is flowing. The direction is set by the engine. When we use like MC delta T for our Qs back when we did calorimetry, we had the possibility where delta T could be positive or negative, depending on what was happening, was it heating up or cooling down. We aren't worrying about that in the second law of thermodynamics. In the second law of thermodynamics, what we are trying to find out is what's the difference in energy. If there's no difference, hot side to cold side of an engine, then no work happened. But if there is a difference, right, then that's the amount of work. This is conservation of energy following the second law. Yes?
Why don't we just use all of the heat for work?
Yeah. Okay, we're going to talk about that. But let's, you jumped the gun just a little bit. We'll get there, I promise. Okay? So just remember that when you're calculating like work for these engines, QH, it doesn't matter if it's positive or negative, you just use the number, right? QC, positive or negative, just use the number, right? We're taking the difference when it comes to an engine. So to start answering the question about like, why don't we just use all the heat in an engine? Remember that this concept and idea of an engine isn't an engineering diagram. It's a theoretical idea, right? Derived out of the second law of thermodynamics. A French physicist by the name of Sadi Carnot, last name right there in the middle, set out to figure out the most efficient engine cycle that could exist in nature. And again, this is not a practical engine design. This is just using the laws of thermodynamics to figure out how to get an engine cycle that will give you the best results. We talked about all the different thermodynamic processes last time, about how we had, what was it, isothermal and isobaric, so constant temperature, constant pressure, constant volume, and then adiabatic processes. So what Carnot did is to get an engine has to work on a cycle. You have to kind of get back to where you started so that the engine can repeat its cycle over and over and over again. If you have just sort of a one-way cycle, you can't get anywhere. Engines have to be cyclical. This is what your car's engine does, right? The pistons go up and down, and they get fired, but then they exhaust, and then they get back to their initial state so that they can fire again. So what Carnot did is he sat down and said, okay, what's the best theoretical cycle that I can come up with, obeying the laws of thermodynamics? And what he came up with was the Carnot cycle. The Carnot cycle consists of, and this is on a PV diagram, okay? It consists of 4 things. We do an expansion that is constant. What's it say? What's isothermal? Constant temperature. Okay? So we do a constant temperature expansion. That's this process right here. And then we do an adiabatic expansion, followed by an isothermal compression, and then an adiabatic compression, and then we're back to where we begin. Okay? This cycle, 2 isotherms, 2 adiabats, 2 compressions, and then 2 expansions and 2 compressions, is the best thermodynamic cycle that exists in nature. You cannot get any better than this. And so what Carnot did is he calculated what the efficiency of this engine would be. So let's talk about efficiency real quick. Efficiency, we use lowercase e to indicate efficiency. Okay? Efficiency, by definition, is what you want divided by what you have to spend to get there. That's sort of like the overall definition of efficiency. If we go back to our Carnot engine that we have right here, okay, what are we spending? Like, what's going into the engine? But think even just like in terms of the symbols on the paper right here. Yeah, QH is what's being spent, right? There's this hot reservoir, this hot side of the engine, and QH is being used to produce what? Work. And so Saudi calculated his efficiency, which he just did work divided by QH. I should use capital. I usually use lowercase h, but that's how I was taught. But we'll use capital because that's what your book does. Okay? So again, this is a way to do it. Okay? But there's an alternative to this one that also works, which is 1 minus QC divided by QH. Now, all of these definitions right here for the efficiency depend on you knowing the amount of energy. Remember, Q is an amount of energy measured in joules. So you have to kind of be able to measure the energy content of your hot reservoir or your cold reservoir, which is technically very difficult to do in a real world application. And so Carnot went a little bit further and defined the efficiency in terms of the temperature. See how in this engine we have hot reservoir and cold reservoir, but then we also have like a temperature, a hot side temperature and a low side temperature. So Carnot went and derived the maximum theoretical efficiency of the Carnot cycle, which again, the Carnot cycle is the best cycle we have in nature. 1 minus the temperature of the cold divided by the temperature of the hot. You need to realize that this efficiency is kind of like, it's a ratio. So it's a unitless value. Because, for example, what you want divided by what you spend. What we want is work in joules, and what we spend is the hot side in joules. A joule divided by a joule is no units, right? Efficiency is also a number that is between 0 and 1. 1 being 100% efficient. Like, how do you get 1 out of W over QH? What has to be true? They have to be equal to each other, right? To get 1 out of this, work and QH have to be the same, right? So that's how you get 100%. In other words, all of the heat got turned into work, right? And there was no exhaust. That's 100% efficient, okay? Carnot showed us why 100% efficient engines are impossible. Brandon, do you think you can see why? Since you asked the question.
Well, it looks like one is like maximum efficiency.
Yeah.
The ratio of cold over the heat.
The cold over the heat. Look at the temperature one. And maybe the clue is that these temperatures have to be in Kelvin. What does the temperature of the exhaust have to be to get 100% efficiency?
0.
Kelvin.
Okay.
So the only way to have a 100% efficient engine in nature is for the exhaust to have a temperature of 0 Kelvin, which is impossible. So another way to state the second law of thermodynamics is that 100% efficient engines are impossible. You will always have some amount of exhaust energy, and that exhaust energy existing means that your engine was not 100% efficient. So it's impossible for us to use all of the hot side, because it means we would have to have an exhaust that had no energy in it.
Why don't we make our engines cold then?
Okay, yes, this is a good question. Okay.
My car not want to start when it's cold. It would be more efficient when it's cold.
Right? Okay. It's not that the engine itself is cold. It's that the exhaust has to be cold. Okay. So let's talk about why the Carnot cycle is the most perfect cycle there is and why it's impossible to do. Isothermal expansions are very easy for us to pull off. Keeping an ideal gas at some same temperature, but just letting its pressure and volume go places, that's a matter of like insulation. It's not a problem, okay? But do you remember what an adiabatic process is? What's true about adiabatic processes? The amount of energy going in or out of the system is 0. So it has to be perfectly insulated. And there's no such thing as perfect insulation. Now, we can cheat. We can cheat that just a little bit. Your car's engine is not perfectly insulated. However, if you do the process fast enough, heat may not have an opportunity to get out. So heat takes time to move from one thing to another, depending on the insulating properties of your material. If you do it really fast, the heat doesn't have a chance to get out, and so we can approximate adiabatic cycles. This right here is called the Otto cycle. I think that's one of the best dad jokes ever, until you realize that it's spelled O-T-T-O, okay? But the Otto cycle is the cycle that an internal combustion engine uses. So this is the actual cycle that your car's engine uses to produce work, okay? And this is from like an engineering point of view now, like the actual practical way that it does it. First, fuel is introduced into the piston cylinder, okay, through a valve at the top, and the fuel is mixed with air. So it needs to be gasoline and oxygen in the air mixed in the correct ratios for it to be the most efficient. Then your car's engine compresses that fuel-air mixture, okay? And in that compression, it pushes all of the gas and the air, everything, and squeezes it right down. when it's at the maximum amount of pressure, the spark plug goes off. And that spark plug ignites that fuel-air mixture, and you get what's called the power stroke. The explosion of that fuel-air mixture pushes the piston down, and that's where you get all your work out. But what's left over is a lot of hot gas, some unburnt gasoline, thermal energy that wasn't used in pushing the piston down. So on the next part of the stroke, another valve opens and pushes that exhaust out into the exhaust system that eventually goes down to your tailpipe and pushed out of the way. So the Otto cycle, I do have a picture of the Otto cycle. Okay, you have adiabats, got 2 of them, okay? And then you got a couple of constant volume processes. So this cycle right here is not the Carnot cycle. Carnot cycle is the best nature can do, period, but we can't pull off a Carnot cycle in an engine, practically, like engineering-wise. What we can do, though, is the Otto cycle, the internal combustion engine cycle, right? And we get a certain amount of work out for the heat in and the exhaust that is put out. So I wrote down on the other slide, this slide right here, all of the different ways we have of calculating efficiency, right? But what the second law of thermodynamics tells us is you cannot have a 100% efficient engine. You can get kind of close, but in terms of real world cycles that can be used over and over again, the internal combustion, the Otto cycle, at best is like 45% efficient. Your car's engine is probably more around 30% or lower. The amount of engineering required to get an internal combustion engine to be efficient is actually pretty high and very expensive, which is why it's never really done. There are other engine designs that are more efficient, but they aren't used because they are difficult to scale properly. And the infrastructure where we have like lots of gasoline stations all around and all that kind of stuff makes gasoline is, for all of its faults and pollution and warming the planet, it does have one huge benefit, and that's its energy density. Gasoline is very energy dense. There's lots of energy stored in the bonds of gasoline, and it's pretty darned easy for us to liberate it and control it. Batteries are nowhere near the energy density of gasoline. So a gasoline car with a big enough fuel tank can have a range of like 600 to 800 miles. And I'm not talking about like a hybrid either. I'm talking about like a standard internal combustion with a 30-gallon gas tank can have a range of 600 to 800 miles. Electric cars struggle to have ranges of like 300 miles, right? And that's with a lot more space and weight taken up by battery. So battery's energy density is not terribly high, which is one of the limiting factors that prevents EV adoption doing what it does, right? There's ways to get around it. We might talk about that in a bit. Okay? But what the second law of thermodynamics teaches us, okay, is that you can't have a 100% efficient engine. To do that, you have to have no exhaust, and the only way to have no exhaust is to have it be at absolute zero, and absolute zero is impossible, even in nature. So let's do an example of just calculating some of these efficiencies so that you know how to work the calculation, all that kind of stuff, okay? Again, none of these problems depend on your understanding of how an engine works. The second law of thermodynamics does not get into the engineering. It's this broad concept of what it means to get work out and the different efficiencies that we have. So what we have, our work is the difference between energies that are consumed and energy that is wasted or exhausted out of a system. And in this problem, we have two different energies. And I like my visualization, I tend to kind of draw this. This is my simplified engine picture, okay? It's not a free body diagram, right? but I know that this is Q hot, I know that this is Q cold, and this is the amount of work I get out. Okay? Just again, visually helps me understand, and then I've got my equations that I wrote down earlier. Okay? So, what is the work in one cycle if we know the amount of energy that goes into and out of this engine? Well, for part A, it's pretty darn it. What's QH?
9,000.
It's 9,000, right? And what's QC?
6,400.
This difference is
2,600.
2,600. Thank you. Answer done. This is conservation of energy, right? Whatever energy is missing got turned into work. All right. Thermal efficiency of the engine. Okay. So now we got to go back and look at our efficiency calculations. They were somewhere over here. Okay. So there's lots of ways to do this, right? We could calculate like what we want divided by what we spend, which for engines would be work divided by QH. Or we could do 1 minus QC over QH. Since in that problem we had all of the Q's. We could also use temperature. Okay? So what I'm going to do, because I already have the work, what I want divided by what I spent. Okay? So what I want was the work, 2,600. What I spent was 9,000. I got, so 29? 0.29 or 29% efficiency. It's not great for an aircraft engine. Tell you the truth. Aircraft engines are actually fairly efficient. Like they'll push 70, 80% efficiency. It's really good. They have to because they lose money if they don't. Okay, then part C, okay? Now they're giving us temperatures, right? So I'm thinking in terms of temperature now, it's that bottom box right here, right? Where the efficiency is 1 minus TC over TH. So my efficiency, 1 minus TC over TH. Whenever you are doing efficiencies, second law of thermodynamics, make sure you are in Kelvin. In fact, for your exam, right, the only place that you can use Celsius is in calorimetry. Okay? Everywhere else, just put it into Kelvin and you'll be safe, right? Heck, in calorimetry, you can put it into Kelvin and you'll still be safe, right? But you don't have to in calorimetry. But everywhere else you do, okay? 1 minus, what's the cold temperature? 450. The hot? This gets an efficiency of 82%. Okay? So 0.82 or 82%. So the initial design here wasn't that great. They only got 30% efficiency, which is really sucky for an airplane engine. And then assuming they can get those temperatures out of the engine, then they should be able to make it work, which this is what they do. Jet engines operate at temperatures that should melt the materials that the engine is made out of. Okay? One of my favorite YouTubers is Dr. Derek Mueller of Veritasium fame. Just last week, he did a video on the materials that go into jet engines. And it's pretty exotic, some of the stuff they're doing to try and make materials that won't melt under the extreme conditions that are in a jet engine. You should go watch it. It's pretty fascinating stuff. But what they'll do is they will run their engines at close to the melting point temperatures of like tungsten and some of these highest, so like 3,000 Kelvin inside of the combustion chamber, and then try to like reduce the temperature or capture the energy of the exhaust that's coming out. The higher an airplane flies, the colder its exhaust temperature is, which is why they fly so high. Less air density, so less friction, cooler outside air temperatures, and so you're capturing more thermal energy in your engine, and you're getting higher efficiencies. Plus the fuel that they burn is pretty clean and contains a lot of energy because it's been refined so much. Before we move on to refrigerators, I just want to plug a little bit electric cars. I kind of dissed them a little bit because of their battery problem, right? But one thing that electric cars have over gasoline-powered cars is efficiency. And nothing speaks to an American like money. So I want to put efficiency in terms of money for you to try and help you understand what's going on when we say efficiency matters in an engine. We're going to normalize my following example to $1. Okay, so $1 worth of gasoline. So you go to the pump and you spend $1 on gasoline. I know you spend more than that, but let's just say you spend $1. Okay, so $1 of gasoline goes into the tank. If your car's engine is, and we'll just throw out a number, we'll be generous, 30% efficient. Okay. How many cents of this dollar was used to move your car? 30 cents. At an efficiency of 30% or 0.3, that means 30 cents was used to move the car. Where'd the other 70 cents go? Out the tailpipe. So if your car's engine is only 20% efficient, how much are you paying to heat the planet and cause air pollution? 80 cents on every dollar that you spend. Okay? This gets worse. I'm not done. Okay? Of the 30 cents that's used to move your car, and again, I'm being generous by giving you the 30% efficiency. Of the 30 cents that's used to move your car, how much of that mass is the passenger? Now remember, the amount of energy that the engine has to put out isn't just moving you. It's moving the entire mass of the car and whatever payload and materials you have in the vehicle. So, what percentage of the mass of a car is you? Less than 1%. Your car probably has a mass, probably has a weight of around 3,000 to 4,000 pounds. If you're driving like a kind of a four-door sedan type car, okay? 3,000 to 4,000 pounds, okay? A couple tons. You weigh not a ton, okay? You weigh in the hundreds of pounds, between 100 and 200 pounds, somewhere in there, right? That is a tiny, tiny fraction of the total mass of the car. And so it's very safe to say that less than 1 cent out of every dollar that you spend on the bus, actually it's more like 1/10 of 1 cent is used to move you. 29 cents is used to move your car, and 70 cents gets thrown out the other end to heat up the planet and cause bad air quality in Fresno. Okay? That's the mathematics of efficiency turned into dollars and cents, right? So the key question is, how do you make it more efficient? What do you do? What can you do right now to make your car more efficient? Not use it. You can't get rid of the engine. You still have to pay for gas, but what can you do to make your car more efficient? What has your mom or dad told you you're supposed to do to take care of your car?
Always get the oil changed.
Get the oil changed.
Look at the tires.
Tire pressure. Okay.
Brakes.
Keeping it clean. Brakes don't help efficiency. Okay. By maintaining correct tire pressure, you can have a big impact on your efficiency, your miles per gallon. That's miles per gallon is the efficiency number that's used in the industry. It's one of the dumbest units in the world. Okay, it's actually close to meaningless because it hides the fact that a change of like 10 miles per gallon to 12 miles per gallon is a much bigger efficiency gain than 30 miles per gallon to 50 miles per gallon. That the 30 miles per gallon to 50 miles per gallon sounds bigger. It's not. If you do the math and you look at the percentages, it's like a 2% efficiency gain, okay? But going from 10 miles per gallon to 15 miles per gallon is something like an 80% efficiency gain, right? So like miles per gallon is one of the dumbest units, and it's used to hide a lot of information about efficiency. The thing you should calculate if you want an apples to apples comparison between things is gallons per mile. Invert the calculation, and then you'll get a very good indication of like how much you're saving. It's much better to take a car that runs at 15 miles per gallon and get it to 20 miles per gallon than it is to get a car that already runs at 30 to 50. So we want to focus on the right segment of the market. Let's now talk about electric cars. Anyone want to guess what the efficiency of an electric car is? Yeah, it's actually over 90%. Okay? Electric motors are very efficient. Okay? And this is a greater than or equal to. Can't go to 100. Okay? But 90% is actually pretty darned easy for an electric motor to get to. Okay? So what does that mean? For every dollar you spend on electricity to power the car, how much of that is being used to move the car? 90 cents. Right? Now, electric cars are much heavier than internal combustion cars, right? So then but still, many cents out of your 90 cents is being used to move you, right? It's just a much more efficient calculation to make. Electric cars also have an advantage in that, well, let's go back to internal combustion. An internal combustion car spends all of that energy to get up to speed, and then what do you have to do to stop? You have to hit the brakes. What do the brakes do? They convert the mechanical energy of motion into what? What energy does it get turned into? Clue, your brakes heat up. Into thermal energy. Okay? It's wasted into the air, into the heat of your brake pads, into causing the brake pads to ablate and send dust into the atmosphere and pollute more stuff, right? Okay. What's an electric car do? How many of you have ever heard of regenerative braking? This is what electric cars do. They have regular brakes in them, but they hardly ever use them. They only use them in emergencies. If you let off the gas pedal in an electric car, the car will recharge the batteries by using the electric motors in reverse. This is a physics 2B thing that you'll learn about if you take physics 2B, okay? But by using Faraday's law of electromagnetic induction, you can slow down the car while recapturing electrical energy. Basically, the motor turns into a generator while the car comes to a stop. So not only are you more efficient to begin with, but you also get to capture back about 70% of the energy you spent getting up to speed to recharge the car. Way better. Full disclosure, I drive an electric car. Because I can't stand cars that have liquids in them anymore. I don't know. I've become elitist, I guess, right? Because like oil change, what's that? I don't understand what you're talking about. You don't have to do an oil change in an electric car. The only thing I haven't had to change it yet. I have to put wiper fluid in my car. Yeah, that's it. Brake fluid. I don't have to put any brake fluid in. The brakes are used so little that I have to check my brake fluid every 6 months to make sure that there isn't too much water in the brake fluid. It's like it stays in the car so long that it can actually soak up water because it's very, very hydrophilic. So got a little brake fluid tester that I test. But that's it. I haven't been to the gas station in years. All right. This is the schematic diagram of but what's the bad side to electric cars? Two very bad things. Okay, three very bad things. Not every electric car is made by Elon Musk. Cost. The price of an electric car, they are expensive. Okay? No, actually, that is not a problem. That is a falsehood. Get that out of your brain right now.
No.
Yes.
Why?
Because internal combustion cars cost more in terms of pollution to produce. I have the hard data to prove it.
But it's still pollution.
Yes, but it's apples to apples pollution. And the internal combustion car is more in its production process. The falsehood that it takes more pollution to create batteries than internal combustion cars is totally false. Yeah, there's way more plastic parts in an internal combustion car. Way more. Anyway, it's cost, initial cost of the vehicle, okay? And the fact that batteries can't take you as far. So range anxiety is a real deal, right? And so people get worried. They buy a car like, oh, I can't go on a road trip with it. Most people use a car every day to go less than 10 miles. Like if you just seriously look at, on an abnormal day, if you're doing a ton of shopping or something, or you need to move something across town, yeah, you're going to use a lot more than that. But those are all use case scenarios that electric cars can easily do. With a 300, 200 mile range, you can easily use your car all day long. It's not a problem, okay? The problem is when you go on a long trip, okay? And now you have to stop, and you have to charge for like a half hour, right? Okay? So these are issues, total issues. But for 99% of the everyday usage of a car, electric cars are no problem. And my response to, well, I can't have an electric car because I need to drive long distance once a year. Guess what? Rent a car. Like seriously, rent a car for that long distance trip. That'll cost you less in the long run than having a car that's less efficient and all that kind of stuff. It's kind of like saying, well, I go skiing once a year, so I'm just going to buy ski boots and wear those all year round. It's the same idea, right? You're just not using the correct thing for the application. All right, I'll get off my high horse. This is a refrigerator. How can you tell it's a refrigerator? Which way is the work going? It's going in, okay? So what we're going to do now is we're going to use energy, okay? And your refrigerator, where does it get its energy from? The wall, electrical energy, okay? So we're going to put electrical energy in, and we're going to use that electrical energy to pull heat out of the cold side and exhaust it out of the hot side. Look at the direction the arrows are going, right? Okay? In our engine, it went in and out this way, right? But in a refrigerator, the work goes in, the hot goes out, right? And the cold goes in. So it's a reversal of the idea, yeah.
So the exhaust is hotter than the food you've been.
That's correct. Where is the hot side of your refrigerator?
The back.
It's on the back, where all the coils are. If you don't know what I'm talking about, then pull your refrigerator out. Be careful. There's dust bunnies back there that are like the size of dragons. Okay? It's got big teeth. Okay, 2 people got it. All right. Go watch Monty Python Search for the Holy Grail. That's your homework assignment over vacation. So what's going on here? So, okay, what do we want? If you're just looking at this diagram right here, what's the thing that we want? If we wanted to calculate, say, the efficiency of a refrigerator. Can you see it? What do you want your refrigerator to do? To cool stuff down, right? So the thing that we want is QC. And what are we getting? What are we spending to get it? Work. So there's the efficiency of a refrigerator in general, okay? Now, because we don't want to confuse the efficiency of an engine with that of a refrigerator, we get all scientific-y and we give a different name to this, okay? And it's called the coefficient of performance, or the COP, okay? Coefficient of performance. The coefficient of performance is just another name for the efficiency of a refrigerator. So you have the efficiency of a heat engine and the coefficient of performance of a refrigerator. Refrigerators, I like writing the conservation of energy statement like this. This will be, your book does it slightly different, but it's the same equation, just written a different way. okay? But I like writing it like this because it reminds me that I'm dealing with a refrigerator instead of an engine, right? So that's what it is. So like, your exhaust is equal to the amount of cold you pulled out plus the amount of work you put in. We're flowing, right? We're pulling energy out of the cold side and we're putting work in. So if we do 50 joules coming out of the cold side and we put 70 joules of work in, how much exhaust do we have? 120, right? It's, again, conservation of energy statement, okay? So we have our coefficient of performance, and then we have sort of our conservation of energy statement. We should be able to make our way through. There's a Carnot refrigerator. Don't worry about it. We don't talk about it. Okay. Instead, you might. Yeah, go ahead.
I forgot it. Can you go back to the other slide? You made me forget by changing slides.
Yeah, that's right. You want me to go back?
Yeah, actually, that's fine. It's
Too late? You don't remember?
No,
Okay.
it's gone. Oh,
You've
actually,
probably seen these stickers on the sides of appliances in the appliance store or something like that. Okay. Again, these are lies. They're useful as a comparison between labels, right? So if you're looking at two refrigerators and you look at it and you see that one refrigerator costs 67 and another one costs 90, what do you know about the efficiency of the higher cost one? It's worse. Costs more money to run, right? That's a less efficient thing. So what they're not good for telling you is that your refrigerator will cost $67 a year. Because it won't. It'll cost more. Because this is based on, if you look at all the fine print, okay, it's based on like an average price per kilowatt hour, and it doesn't take into account all the different things the PG&E charges you for and all that kind of stuff, right? So estimated yearly electric use, that's fairly consistent, but the prices are going to be way out of whack, okay? But the energy guide label does let you compare like refrigerator to refrigerator, right? Or TV to TV, right? The lower the dollar amount, the more efficient the device is. So that's your take home from these labels. Don't think that it's only going to cost you $67 to run your refrigerator, because it's not. Maybe if you live in the middle of Arkansas, in the middle of nowhere or something where they have plenty of power and no other costs, right? But here in California, it costs a lot. All right, what are we at? Like 30 cents a kilowatt hour now or something? 20 cents a kilowatt? It's pretty expensive. Okay. National average is something like 12 cents a kilowatt hour. So like, yep. Well, it's California too. Your refrigerator. Got a cold side and a hot side. Like I said, the hot side's on the back or bottom, sometimes the top, but usually the bottom or the top, or the back, right? And basically what happens is you take an engine, an electrical engine, okay, and it compresses gases that are inside the cooling tubes inside of your refrigerator. And it compresses that gas, and whenever you compress gases, they become hotter, okay? And so that compression, right, goes into a hot side called the condenser, okay, where that heat is then, where does the heat go that your refrigerator pulls out of all your food? It goes into your kitchen, okay? Humans are so amazing. We'll cool off our food in a box that makes our kitchen hotter, so we'll run an air conditioner. Yeah, I think that's how it goes, right? Then it goes through a valve where that condensed hot stuff is allowed to expand. And what happens when a gas expands? Cools off, okay? And then that will make its way back to the condenser, or the compressor, where it'll compress it back up again. Again, we're putting energy in to cause this phase changes and all these changes within the gas, but we're taking advantage of thermodynamics in that we can expel the heat into the room and then draw heat out of the inside of the refrigerator and then repeat that process again and again. You've probably heard your refrigerator kind of kick on and kick off, right? You're hearing the compressor, okay? Little buzzy noise, right, as it runs, compressing the gas. What's this? It's an air conditioner. In other words, it's a whole home refrigerator. Okay? Because an air conditioner has a hot side and a cold side. An air conditioner, what side do you want the cold side on? The inside or the outside? You want the cold side on the inside, right? But in order to get that cold to be cold, you need to get the heat out of it. And so where are you going to push the heat? To the outside. Refrigerators, whether they're air conditioners or actual refrigerators, are called heat pumps. What does a heat pump do? It pumps heat around, okay? My home has a heat pump. Our furnace that was 27 years old finally gave up a few years ago. It was the original furnace for the house. Horribly inefficient thing. I hated it. Cost me so much money. I was one of those dads that ran around and told everybody to wear sweaters and die in the heat because I'm not paying money for this. We replaced it with a heat pump. At the time, it still is illegal to install new furnaces in homes, gas burning furnaces. You have to install electric heat pumps because gas burning furnaces are dumb and inefficient. So we went for a heat pump, and the heat pump that I picked, I was like, I want all the efficiency documentation for these. And the installer was like, what? I was like, don't worry, just contact your sales rep and ask him for all of the efficiency documentation. He'll give you a bunch of PDFs, just email them to me, don't worry about what they say, right? And I went for a deep dive, like on all of these manufacturers, all these different kinds of things. Got the most efficient heat pump I could get for the money and for the size of my house. I have gone from, you're gonna burn to death or freeze to death, I don't care, stop complaining, to, oh, you want it to be a sauna in here in the winter? That's fine. You want it to be, sub-zero in the house during the wintertime? I'm good with that. Because my heat pump is so efficient that I feel like I'm making money off of it. It's not true. But my old air conditioner would take 6,000 watts, anywhere from 4,000 to 6,000 watts while it was running. Okay? My heat pump at full blast, whether it's heating or cooling, takes 1.2 kilowatt, 1,200 watts. It's like, yeah, it's like 4 to 5 times more efficient than my old system. So it works. I can go on the same day, I can go from cooling mode to heating mode because all the heat pump does is it reverses the direction that it's pushing coolant, right?
Is a heater just a fridge in reverse?
Yeah. So what I'm doing right now, today, at my house, is I am pumping cold air where? Out of my house. I can go stand next to my heat pump's condenser and there's a bunch of cold air coming out of it, right? So where's the hot air going? Inside the house. And when I want to air condition my house, what do? I just push the button and it reverses. Right? It's just the control thing on the wall. And I just say, turn into an air conditioner. And then it just basically puts the cold air on the inside and the hot air on the inside. Has the added benefit of an air conditioner runs basically in like 1 or 2 settings. There's like a kind of a low mode and a high mode. My heat pump is infinitely variable. It can just decide how much heat it has to pull out or put into a space. And it keeps track of how the temperature varies in my house. After about a week, it had learned everything about my house, and now I can set the temperature in my house to within like 0.2 of a degree of where I want it. Yeah, like it's crazy good at maintaining that. Highly recommend a heat pump. If anybody you know or love needs to change out their system, tell them to get a heat pump. It's going to save them money in the long run. Again, problem, higher upfront cost. Right? But you save that money like nobody's business. And then I threw a bunch of solar panels on top of my house, so it basically more or less runs for free. So, the advantage of being able to afford things like that. You'll get there. I promise you'll get there. You're in the right place at the right time, doing the right thing. You'll eventually get to the point where you'll be able to afford these things. Don't let anybody tell you that your future is doomed. Okay? My generation's screwing it up for you, but there's some of us that are fighting for you.
Is your heat pump DC or AC?
Well, they're all DC eventually, but AC goes into it.
But DC comes out of
The heat,
solar panels, right?
the solar panels produce DC, which then gets turned into AC,
And then back to DC.
and which again turns back into DC for my heat pump.
Direct DC from the panels to the
No.
heat pump? That's lame.
Yeah. So there's losses there, but.
Efficiency.
All right, let's do some calculations with the coefficient of performance. All right, what are we told? We're told that the coefficient of performance is 2.10. Okay. Again, no units on that. It's an efficiency number, right? Coefficient of performance, by the way, can go above 1. Don't think about it. Just accept it and move on with your life. Okay. Efficiencies in engines can never be over 1. They always be less than 1. Coefficient of performance, I think the worst coefficient of performance is 1. And then things get better as you go up. All right, so what do we got? So there's an absorption of heat from the cold reservoir. So of all the things that we could be writing down, where were they? Right here, okay. We have our coefficient of performance, which is QC and work, but then there's these 3 things, right? We've got the QC, which is QL on this diagram. QC coming up, we've got work going in, and we got QH coming out of our refrigerator. Again, what I like to do sometimes is I just draw my engine, and I go, okay, QC in, work in, QH out, right? This is my little schematic to keep me oriented between an engine and a refrigerator. Okay, this 34,000 joules of heat has to be one of these 3 things. You can guess and have 1 in 3 chance of getting it right, or you can be smart. Where does the 34,000 joules, where is it supposed to be? Is it work? Is it the amount of work we're putting into the engine? No. Is it exhaust? Is it what's coming out of the refrigerator? No. What does it say? Absorbs 34,000 joules of heat from the cold reservoir. So the 34,000 must be this leg right here. If it wasn't, if it was the exhaust, it would say expels or extracts energy, right, into the surroundings. That's what the language would be for that. So I'm going to assume that my QC is 34,000. And if I know my coefficient of performance, can I figure out what my work is?
Yeah.
The mechanical energy required. So we know that the coefficient of performance is equal to what we want, QC, all over what we spend, which is the work. So that means that I can solve this for the work. The work is QC divided by the coefficient of performance, which is 34,000 divided by 2.1, which is 16,200?
Yeah.
Right? There's the amount of work that went in. Okay, and the mechanical energy required each cycle. And then how are we going to find out how much heat is discarded?
QH is equal to QC plus W.
Right? This, by the conservation of energy, the amount of heat coming out has to be the sum of the 2 things that went in. So that's going to be 34,000 plus 16,200. 5,200? 52,000?
Wait, no, it's 50,000.
50,200. I missed a 0 in my calculation in my head. This is why you should never do calculations in your head. Okay? All right. So are the calculations here hard? No. It's the keeping track, right? It's the making sure you know which one's QC, QH, all that kind of stuff. And follow the concepts behind it, and you'll be okay. All right. So heat flows from hot to cold, or at least spontaneously flows from hot to cold. And another way to say it is that there's no such thing as a perfectly efficient engine, or refrigerator.
I remember my question from earlier.
Yeah,
I keep on saying that heat is absorbed or anything, but I thought heat was a transfer.
it is, and that's where we go wrong, right?
So what we're saying is technically wrong.
Yeah. We're saying a heat transfer, or an absorption transfer. It's weird, but it is the way it is. Humans are dumb. But there's another way to talk about the second law of thermodynamics, and that's entropy. Now, don't panic. If you've been in chemistry, we're not going there, okay? We're going to take this from a different point of view because entropy is often talked about as like the disorganization in a system, but that doesn't mean anything to me, right? I tried to argue about entropy to my mom in cleaning my room. I was like, Mom, the universe is just going to always increase its entropy, so I'm just helping it. She was a biologist. She didn't buy it. I had to clean my room. So this whole organized, disorganized thing can be useful, but it doesn't really get to the whole essence of what's going on with entropy. When I was growing up in Santa Cruz, where we're all hippies and tree huggers and all that kind of stuff, I was told that we were going to run out of fossil fuels by the year 2000. That we were like, there was just going to be nothing left, and it was, everything, we were all going to die and go back to living like cavemen or something. And when I became a physicist, I was like, not only does it not sound right, it sounds completely wrong. Because what's one of the things we know about energy? One of its chief features. It's always conserved. Always conserved. And so you can't destroy energy. What's the only thing you can do with energy? Transform it from one form to another. So entropy is a way of keeping track of what useful forms of energy are. And by useful forms of energy, we're saying that humans can use it to do something, namely work. On the screen, I have a chart, a ranking, if you will, of useful to less useful forms of energy. The most useful forms of energy are here at the top. So most useful to least useful. Notice what's at the top. Mechanical energy, the energy of motion. Okay? The energy of gravitational potential energy. These are all things we've been studying this semester, and they're exceedingly useful to us. We can use these forms of energy to do a lot of work. Okay? Next, most useful is electrical, followed by nuclear, then chemical, and you can see that I've given a lot of space before we get down to thermal. So let me show you how you kind of think your way through this chart and think your way through entropy. Let's take your car's engine as an example. Okay, internal combustion engine. What kind of energy is stored in gasoline? Yeah, which kind though? Chemical potential energy. Okay, so we burn that chemical potential energy, and what do we make? Mechanical. We make the car go. The corresponding cost of thermal energy is very large because we had to climb the ladder. If you climb the ladder, you pay an enormous cost in thermal energy. Notice electric cars, the electrical is very close to the mechanical on this hierarchy here. Okay? And so we don't have to go as far to get from electrical to mechanical. We're very efficient at that, which means not very much heat is produced. There is some, okay? But not nearly as much as the heat is produced as chemical. And let me ask you a different question. When was the last time you saw a car rolling down the street powered by air temperature alone? Never, okay? Thermal energy is a really bad form of energy. We use it all over the place. All of our power plant, all of our fossil fuel and nuclear power plants basically turn their fuel into thermal energy to then make electrical energy. So engineering-wise, turbines and things like that, they need thermal energy to function. More efficient are things like wind and solar and hydro, because those are direct. You're turning direct mechanical energy into electrical energy. You're not producing very much waste heat. Okay? But fossil fuel power plants generate a ton of waste heat and pollution. Nuclear is actually the only one that doesn't produce any pollution. It is zero pollution, zero carbon, 24/7 electrical power. I'm a big fan of nuclear power. I know it produces radioactive waste, and that's a really good conversation to have, but it is nowhere near the amount of waste when you take into account air pollution that comes from fossil plants. If I was allowed to, I would build a power plant in my backyard. Like, seriously. And I would run that, okay? Forget solar power, nuclear power, 24/7, okay? I'd let my kids play on it. They are so safe at various scales. What makes nuclear power unsafe in our society today is our government, because we haven't innovated nuclear power since the 1970s. All of our reactors are running on outdated theory and technology because 3 Mile Island and people got scared. And anyway, it's an example of the power of the press is what that is. So entropy is a good way of thinking about how useful energy is. So when people run around and say there's an energy crisis, we're going to run out of fossil fuels, which, by the way, we're not going to, not for at least the next 300 years. What are we talking about? What's really the crisis? It's an entropy crisis. We're really good at extracting chemical energy from gasoline. Like, our engineering's pretty good. It's not efficient, but our infrastructure is built so that you can walk just about a quarter mile in any direction from this building and find a gas station. How many electric charging stations can you find in a quarter mile? The answer is 0. Well, there's a couple here at Fresno City College, right? But they're the wimpy ones. They don't charge cars very well. Okay? So there's an infrastructure problem, right? There's a money problem, right? It's really easy for us to fill a tank of gas in 5 minutes. It takes a half hour to charge up an electric car, right? There's all these different issues that exist. But they're all entropy issues. And entropy is all about efficiency and cost and all of those sorts of things. I believe that the role of government is to enact policy so that we can transform our society to better states, right? It seems like the current government, if I can get a little bit political here, is trying to do the reverse of that, right? Bring back all the old ways, right? Because the old ways were better. No, right? They're polluting. We're killing people with air pollution. In our country and other countries. And so the faster we can get to cleaner sources of energy, the better. And that's a great thing for government to be involved in, because corporations won't spend money on something if they don't have to, right? But governments can. So you incentivize, you get the problem, you get the ball rolling, and things will happen. And it is happening. It's happening right before our eyes. I just wish it would happen a little bit faster so that human suffering could be a little bit less in the transitions that we have coming up. Comic strips, kind of an old-fashioned idea. I don't know, do people read comic strips anymore nowadays? Not really. I mean, mostly it's, TikToks and memes and that kind of stuff, right? But it is kind of nice to know you're on the winning side. Human beings are basically organizational creatures, right? We're constantly organizing things. We are, and I'm not just talking about you and your obsessive compulsion to clean things up. I'm talking about we take food in and we build up structures in our bodies, and then we put the waste out, the stuff that we can't use. We organize by building buildings and all that kind of stuff. Entropy in the universe wants to decay all of that down, right? And one of the ways of talking about the second law of thermodynamics is that you must pay a price, right? For all natural processes and even forced processes, the amount of entropy will always increase. Ultimately, where do we as a species and a planet get our energy? The sun is the answer. All of our energy comes from the sun, okay? Nuclear could be argued to be independent of the sun, but basically the elements are there from when the sun was created, so we got it from the sun. In the protoplanetary disk that formed, it was stellar material. So we get it from the sun. So that means the sun is gaining entropy. It's running out of its fuel. Don't panic. It's going to take a few billion years to get there. Okay? So we won't be around to see it. But we're always, even as we organize, even as we try to put the energy into certain forms that are easy for us to use, we're always kind of falling behind the ball. We can't break that rule, but we can certainly organize a lot better. Okay? Is I guess the message that I am trying to put out there. That's all I have for chapter 15, right? Well, thank you. So good luck on your final. I'll see you guys next semester. No. What's going on tomorrow?
You're sick.
I'm sick, right? There will be no lab. Your other classes will be happening, right? But I'm going to be sick. I'm actually going to the doctor for a physical. And then what's happening when we get back on Tuesday? Exam review for the exam that's happening on Thursday. What's happening Wednesday? No, we're just going to do GRASP that day. Okay? Yeah. More review. Yep. Because no, we're not doing that one either.
Took that off of Canvas, and I was very upset.
Yes, it's all gone. All right, have a great Thanksgiving. Be safe. Come back to me in one piece.
I'll come back in a bigger piece. How about that?
Oh, a bigger piece is good.